Alright, how's everyone feeling?
Good.
Any reminder, we do have a normal lab this week, so do report to lab as normal. It's going to be about work and friction, mostly friction. And for lecture, really all of this week, we're going to continue talking about rotational motion. Any questions, needs, concerns from you guys before we get started? Last time, the last concept we introduced is that of centripetal force and the centripetal acceleration that it causes. We began discussing how in each of these images there is a force that is making an object start turning in a circle, given that, according to Newton's first law of motion, a lot of objects don't really want to move in a circle. At the very least, they don't usually want to orbit something else. In each of these cases, there is something being forced to orbit a point outside of itself. All these items, the can, the moon, all these cars want to move in a straight line, but cannot because of the presence of a force acting on them in a centripetal manner. In each of these pictures, there's a different force causing the circular orbit to happen. In the case of the can, it's the string's tension pulling on it. In the case of the moon, it's gravity pulling on it. And in the case of a car turning in general, the force that causes it to begin entering a turn is you changing the direction of the force that the tires apply to the road. And so in all of these cases, all of the objects are accelerating centripetally because by turning over and over again, they are constantly accelerating. The act of rotating in this way, the act of orbiting, is an acceleration. And we call this specific type of acceleration centripetal acceleration, because the word centripetal, again, means center seeking. All of these objects are accelerating towards the center of their orbital path, but they keep missing it because in addition to being forced towards the center and accelerating towards it, all of my markers. Someone has messed up my filing system when they used my board over the weekend. How inconsiderate of them to not factor in the filing system that I told no one about. In all these cases, the objects have a velocity, they want to move in a straight line. And so constantly turning does necessitate there be an acceleration, because normally linear velocity dictates they would want to move in a straight line this way. In order to change direction, you have to accelerate. So constantly changing direction and moving in a circle instead of a straight line is an acceleration, and that acceleration has to be caused by a force. So when I say centripetal acceleration, I am referring to the object constantly changing direction. Its linear velocity is constantly changing direction. And the number for centripetal acceleration is less a measurement of how much its speed goes up or down, and more a measurement of how much the object is constantly changing direction every single second. If I asked you to calculate centripetal acceleration and you got a very big number, it means the item is changing direction very rapidly. It would be making a lot of laps very quickly. Whereas a very small centripetal acceleration number would indicate that it's not changing direction all that fast. Like the moon technically has a very low centripetal acceleration because it takes it a whole day to make one lap. We'll look at some numbers for that later. But every centripetal acceleration has to be caused by some real force. Whenever one object is turning, moving in a circle around something, some real force has to be acting in the role of a centripetal force. and that centripetal force will cause centripetal acceleration. So this first formula here is just a slight tweak of Newton's second law. It's just saying that the centripetal force causes centripetal acceleration of the mass, and that centripetal acceleration is equal to linear velocity squared over the radius of the circle. You have to apply a certain amount of force to generate the correct amount of centripetal acceleration in order to get the item to spin in a certain circle of certain radius while moving at a certain speed, velocity. And since the object is technically rotating, you can instead describe its motion using omega, angular velocity, and there's just a slightly modified formula if you wanted to use omega instead of v. So all this to say, again, if it's spinning in a circle, it is constantly turning, there's a force responsible for that. And how do you guys feel on the concept before I start applying this to a few examples of things you experience in the real world? All right. Let's kind of start by putting some numbers to, namely the scenario with the can on the string, or alternatively, this rubber cork on a string. If I take this object and just swing it in a circle above my head, the cork again wants to move in a straight line, and the string is kind of physically acting as a leash, keeping it at a certain distance from my hand. It can't get any further away, even though it's trying to escape. And as a result of moving forwards, trying to escape, as the string is constantly pulling it towards my hand, it moves in a circle, not getting any further away, but still in motion. And this is the scenario we're going to put some numbers to, just to demonstrate how those work. We've got a 1 kilogram mass hanging from the end of a 1 meter long rope. We would then swing it above our head in a circle, and the object is going to have a linear velocity, linear speed, if you want to think of it that way, since direction's not much of a, going into details I don't need to. Linear velocity of 3 meters per second. So here's our item on a string. The string is 1 meter long, and so that is the radius of this giant circle that we are forming. The length of the string is the radius of this circle. So that's why we're going to take the length of the string and use it for r in our formula. Just want to make that clear. I have a few students asking why I call it a radius. It's because it is the radius of this giant circle. Mass of 1 kilogram, string length, radius of our circle is 1 meter, and the object's linear velocity is 3 meters per second. Now that's the speed that it wants to move at in a straight line. If I snap the rope, the object is going to fly away in a straight line 3 meters per second. My first question, given this information, is what must the object's centripetal acceleration be if it is constantly turning to stay in this 1 meter radius circle? Formula for centripetal acceleration from the previous slide is v squared over r. Our velocity is 3, our radius is 1, and so the required centripetal acceleration is going to be 9 meters per second squared. This is an acceleration, so it shares the old acceleration unit we've been using since the beginning of the course. It's just a specific type of acceleration. And this again tells us how quickly the mass is changing direction. Bigger centripetal acceleration means it's changing direction very rapidly. It's probably going to be making a lot of laps very quickly. Whereas a very small answer for this indicates It's not changing direction as fast. It's not taking that many laps in a moment. But that is the needed centripetal acceleration of this mass when going around this circle. Questions finding this number. All right. Now, this centripetal acceleration is being caused by a centripetal force. All motion like this is due to a force making it happen. Because again, this thing wants to move in a straight line. There has to be a force making it behave this way. And in this particular scenario, the force playing the role of centripetal force is the tension in this string, because the string is what is keeping the mass 1 meter away from our hand. The string is, and the force within the string is what is forcing the mass and keeping it at this distance from us. So the tension in the string is playing the role of centripetal force. I find occasionally this is one stumbling block with centripetal force, because unlike friction, it's not always going to be the same thing behaving exactly the same way each time, or like how gravity is always found the same way and always does exactly the same thing. Centripetal force is a role that multiple types of force can play. Any force can hypothetically act as a centripetal force. It's like a part in a play. In this case, the rope tension is playing that part. And again, in the case of the moon, it's gravity that plays that part. So you can solve for centripetal force using the formula from the previous slide, Fc equals m times AC. But what is playing this role is just going to kind of depend. We're going to look at different examples and make it clear exactly what type of thing is acting in that part. In this specific case, it's the tension in the rope that's going to be playing this part. And since we know the mass of our object and we found the centripetal acceleration, we can confirm how much centripetal force is present here. Fc equals our mass of 1 kilogram times the centripetal acceleration we just found a second ago of 9 meters per second squared, and the amount of centripetal force tension in the rope in this moment would have to be 9 newtons. If the rope has to be exerting exactly 9 newtons of tension in order for this to work. If the rope can't handle that much tension, like say it's just a single piece of twine that's going to snap at 7 newtons, the rope would snap and the object wouldn't be able to orbit like this. This tells us not only how much force is required, but how much force the rope has to be able to handle. You guys feel so far? Now, while I've got this example up, I want to kind of ask a few hypotheticals to kind of show how the relationships of the numbers work. Let's say that we've got this same object, mass of 1 kilogram, the rope is still 1 meter long. But let's say that we just choose to make our hand swing faster. So let's say this is what we were just doing, and now I'm just choosing to speed it up. So let's say, hypothetically, instead of 3 meters per second, I kicked the speed up to 6 meters per second, twice as fast. How would that change this? It will quadruple it. Very good. And that's because the centripetal acceleration formula squares the velocity. So if we plug in twice as much velocity, the centripetal acceleration is actually going to quadruple. So instead of 3 squared, giving us an answer of 9, it'd be 6 squared, giving us an answer of 36. And as a result, we would then take that centripetal acceleration plug it into the centripetal force formula, and get a required centripetal force of 36 newtons. I almost misspoke there. So not only does the centripetal acceleration quadruple when you double the speed, the needed centripetal force, hang on, trick myself up. The needed centripetal acceleration quadrupled, and so too does the force. Meaning that if you double the speed at which you're swinging this thing, the required amount of force quadruples. The string has to be exerting 4 times the force. And in turn, you also have to be exerting 4 times the force to make it happen. The string has to be able to handle 4 times more force. Again, if this thing's gonna snap at like 20 newtons, it's gonna snap and the cork is just gonna fly away in a straight line. So the faster you make a turn, the more forces are involved. The more force is required to make the turn while moving very quickly. Have you noticed that when driving a car? If you are driving responsibly and legally, you tend to slow down a lot before making a 90-degree left or right turn, right? Very rarely are you going at 40 and you stay at 40 around the turn, because that tends to be somewhat out of control. It takes a lot of force, and your engine physically might not be able to put enough force between you and the road to make it work right. You slow down first. And that's because turning in a car still requires centripetal force. A 90-degree turn in a car is just choosing to enter this orbit for a quarter of the turn before exiting it. Turning in a car requires centripetal force, and you slow down to reduce the needed amount of force to something that you can actually generate between the road and your tires. So, the faster something is moving, the more centripetal acceleration and force is required in order to make it turn. And that is, again, why you tend to slow down to better control your turns in a car. Does that make sense as an application of this in real life? All right. Now there's one more tweak I want to make to this as an example before moving on. So I'm rewinding. We're going back to a velocity of 3 for a moment. So back to the original numbers as presented. Now, instead of doubling the velocity, let's double the radius instead. We are now going to make the string twice as long. So our radius is now going to be 2 meters. What effect is that going to have on all of our calculations? If our radius doubles, we're going to divide by 2 instead of by 1. That's going to cut our centripetal acceleration, and therefore the centripetal force as well, in half. By increasing our turn radius, the centripetal force requirement actually drops. And that's why very narrow, tight turns are also usually pretty dangerous. If we had instead reduced the radius, maybe divide by 1/2, that would end up doubling the amount of force required. So very narrow turns, a very small turn radius, also require a lot of centripetal force. And that's why you don't tend to notice the force requirement if you're just kind of like banking on the highway. Like if you've got a very long distance to slowly drift into a new direction, you don't tend to think about it that much. You don't notice the centripetal forces for that. But if you're doing a very quick 90-degree turn on a town road, or just doing donuts, I guess, that's a very small turning radius. It requires more force, and that's why you slow down for it. So the faster you make the turn, the more centripetal force is required. The narrower the turn, the more centripetal force is required. Again, kind of just advice for driving. But I can kind of demonstrate it a little bit with this thing. I can get an interesting effect if I just make the rope shorter. The rope's not actually going to exert all that much more force, but instead, because the rope is shorter, the object's just going to speed up for that same amount of force. So I'm not going to change what my hand is doing, I'm just going to shorten the rope, and it speeds up. So there's an interesting interplay of all the variables here and how it affects cars. It also ends up affecting planes, for one thing. If you've ever watched any amount of piloting media, like Top Gun or something like that, you might be aware that planes banking, like fighter jets, banking too fast has a tendency to knock out the pilot. Sound familiar? That happens because when the plane turns, the plane has to have a certain amount of centripetal force acting on it, and in turn, so does the human inside of it, because the human has to turn with the jet. And the faster the jet is turning, and the narrower the turning radius, the more centripetal force is required, both on the jet and on the pilot. And when humans are exposed to lots of forces, that can knock you out sometimes, especially if all your blood flows away from your brain. So, if that sounds familiar, that's related as well. Questions thus far? All right. I got one more number example, and it's actually about a fighter jet. So, we'll just put some numbers to this and then try to sum up all the concepts here. Fighter jet has a mass of 200 kilograms, sorry, 2,000 kilograms, my mistake. 2,000 kilograms, which is a lot. That's about 2 SUVs lumped together. And it's flying at Mach 2. Mach indicates speed of sound. Mach 1 is the speed of sound. Mach 2 is twice the speed of sound. And so twice the speed of sound, just to go ahead and give you the number, is 686 meters per second. Usually. The fighter jet is going to turn, and in order for it to turn, there has to be a centripetal force acting on it. The centripetal force on a turning plane, kind of like how a turning car requires you to change the direction of the force between you and the road, a plane has to bank in order to change the direction of the lift force acting on it. When it banks, it literally redirects some of the up and forward force into an inward force to generate its own centripetal force. That's why they physically have to turn, change the direction of their wings to change the direction of the forces. So this pilot is going very fast, going to turn, bank the wings, change the direction in order to generate centripetal force and cause this turn. The jet requires a lot of centripetal force in order to turn. That means there's also going to be a lot of force on the pilot. This particular pilot is able to withstand a maximum centripetal acceleration of 85 meters per second squared before knocking out. Again, there's a certain amount of force and acceleration a human can handle while remaining alive and conscious. So I'm just going to use this picture for this one. Mass to 1,000 kilograms. Velocity 686 meters per second. Per second. That's the end of that unit. Our required centripetal acceleration, our maximum centripetal acceleration when making this turn is 85 meters per second squared. That's the highest this centripetal acceleration can go before unconscious and bad things happen. And at that maximum turning rate, what is the turning radius of this jet? What is the radius of the circle that it is forming in the sky? Big number, yeah.
5,536.
Yep. Bless you. Centripetal acceleration is v squared over r. We know the maximum centripetal acceleration we can handle, and we know the speed we're moving at, so we can figure out what our turning radius would be in this scenario. So 85 is going to be equal to 686 squared over r. Therefore, a little bit of algebra, r is going to be equal to 686 squared over 85. And remind me again what that answer is.
5,536.
Turning radius of 5,536. Just double check that myself. But yeah, it's meant to be a big answer. Calculate. 686 squared. 85. Yep. Over a 5 kilometer turning radius. And you thought your truck's turning radius was bad. This is true of most things that fly, because most things that fly are moving very fast. And therefore, in order for the centripetal force to not be too big, they have to make really big turns, very big turning radius. If you've ever flown in a commercial aircraft, you might have noticed that once you take off, you tend to bank slightly, and then you're turning around the city in a giant circle for a long time before you level out and then head towards your destination. Commercial aircraft have giant turning radii as well. In fact, they take it slower so that they can have a smaller turning radius. The jet moving so fast is what increases the required radius in this particular scenario. So, jets and planes are incredibly quick, but their turning radius is pretty bad. So, just another example to kind of show how these factors are related. Questions, feelings, concerns? All right. Now, admittedly, centripetal force is kind of a weird concept. I do find, again, that the rotation stuff in general is kind of weird if people are used to thinking in straight lines. So again, any questions, any concerns at any time, I want you to make me aware of it. I want to address your questions. The main things that I want you to know and take away from this part of the course is that if something is turning, there is a force required. And the faster it turns and the smaller the turning radius, the more force is required. Yes?
How did you get the formula like that? Like the 686 squared over 85?
Yes. The R is on the bottom of this side, so to get it in the top, I'd have to multiply both sides by R, which would technically then look like 85R times 686 squared. And then to get R by itself, divide both sides by 85. Does that answer the question? Okay. Again, main takeaways that you guys should have from this for your daily life on planet Earth. If you want to turn, if anything is turning when it wants to move in a straight line, there is a force required to make that happen. And you need more force to turn quickly and over a smaller radius. If you take the turn slower and over a bigger radius, there's less force required. So, caution while driving. Sound good? Okay. Now there's one last concept related to this that I want to begin discussing. And I'm bringing this up to clarify all the terms and compare it back to what you've noticed in real life. I asked when we started talking about this if you'd heard the word centripetal force and acceleration before. It's okay if you hadn't. My next question, though, is if you've instead heard the term centrifugal. If that word sounds familiar. It's okay if it doesn't, I'm just curious. The thing we have been talking about is centripetal. I'm I'm enunciating it weird to make it clear what letters I'm saying. We have been talking about centripetal, and that is the actual force that makes things turn. Centrifugal is something else. And I'm bringing it up again to make sure that the terms are clear. Centripetal force is a real thing that really makes things turn. Centrifugal force is something else. I've been drawing the comparison to cars turning a lot for this section of the course, and so I'm going to do that some more. You ever notice that when you do take a turn too quickly, like say your velocity is too high and therefore there's a lot of centripetal force required, when that turn happens too fast, like say your car is turning to the left, what direction do you feel like you're moving in your seat?
Right.
To the right. That's what you feel in your body, and you might even feel like car turns too fast to the left and you get yanked to this side of your seat and it's a struggle to keep the wheel over there. Again, don't actually take a turn too fast, but if it's happened, does that sound familiar? Okay. That phenomenon is what centrifugal force is talking about. The term centrifugal means center fleeing, whereas centripetal means center seeking. The centripetal force is the real center seeking force that is making you and your vehicle turn. There is a real force pulling you to the left towards the turn. But you still kind of feel like you're getting pulled to the right, correct? That feeling is the centrifugal force. Again, this is real, this is actually happening, but you still perceive the force being in the other direction. That's what the term centrifugal force is referring to. And the thing is, you're not actually being pulled to the right. You do feel like you do. I'm not arguing with your senses and your experience. What I'm saying is there's not actually a force pulling you to the right when you make a left turn. There's not a force pulling you to the left when you make a right turn. Did I mix that up? What's happening here is Newton's first law. The law that says an object at constant motion will remain at constant motion until acted upon by an outside force. You are not a part of your car. You are a separate object, right? And so once the car starts turning, that does not necessarily mean you immediately begin turning with it. You are a separate entity. And so your car is starting to turn to the left, but you are your own being with your own inertia. And your inertia wants to keep moving forwards. That's the premise of inertia, remember? If your body is moving north in a straight line, your inertia wants you to keep doing that. Even if the car beneath you starts turning to the left. I'm gonna repurpose my drawings here. All right. Poorly drawn car, turning to the left. You in your car, you want to keep moving north because that's what your inertia tells you to do. And so even though the seat beneath you starts moving this way, your inertia says go that way. And what you end up feeling is that the seat and the seat belt that you're stuck to yanks you this way, and your whole body jerks in this direction, which isn't technically to the right, it's to the north, but it feels rightward from your new leftward moving perception. Your inertia wants you to go that way, you're being forced this way, and that feels rightward from your new reality. sorry, yeah, that feels rightward given that your body is now being yanked to the left. The actual force acting on your body points leftward towards the center of this circle. It's just that your body wants to move forward, and that feels like a force to the right. So when I mention centrifugal force, this isn't a real force. That's why the notes here call it fictional. There is something, you are sensing something. I'm not arguing with that. It's not like a trick. You're sensing something. It's just not an outside force pulling you to the right. So it's a fiction. It's a thing. It's just not a force. If that makes sense. People use the term centrifugal force to refer to this phenomenon. It's just not really a force. Your body wants to keep moving forwards, and so once you get yanked to the left, your body wants to move right, and that's where the perception is coming from. But it gets even more complicated than that, because you're being pulled to the left. You think like you're being pulled to the left, right? Trouble is, not only are you a separate thing from your car, your body is not really one object. You are a bunch of bones, meat, and fluids stapled together inside of a skin sack. Sorry for the image there. You are not really one thing. All of your limbs and all of your blood have their own inertia. And that's why if you make a turn too fast, sometimes your arms kind of go out with a mind of their own. They have their own inertia, and they are being yanked at your shoulder, but their own inertia causes them to kind of experience centrifugal force as well. When your body gets yanked to the left, all your limbs and all of your blood also want to move in a straight line, so they try to. You might notice on a fast car or on a tilt-a-whirl that your limbs sometimes seem to have a mind of their own and go in the direction your body would normally go. And what ends up happening, why you feel like there's a rightward force, is that your blood tries to go this way, and it then pushes in this direction against your skin. Because it's trying to escape. Your blood's trying to leave your body. Because it has its own inertia. And since it has its own inertia, since it's pushing rightward on your skin, that's what you end up feeling. Because your entire perception of force is based on the nerves in your skin. You cannot perceive force outside of how it acts as a pressure thing on your skin cells. You don't have a force detector, you've just got a pressure sensor in your skin cells. So all you're really feeling with your nerve endings is your blood pressing this way while your body's getting yanked this way. So the rightward feeling force is your bones and your skin going this way, trying to exit your body as you are getting hauled to the left with your car. Weird, right? You can kind of simulate this a little bit if you just swing your own hand around too much, because eventually you'll notice your blood pooling up in your fingertips. So if you ever want to try that out on your own, you can. This is very similar to the device known as a centrifuge, the machine that you put test tubes in and they spin, and then all the bits in the fluid separate down to the bottom of the tube. Sound familiar? It's doing the same thing. All of the particulates in the fluid have their own inertia, pushing them to the edge of the container. The container is actually exerting an inward force to keep them in the container, but their own inertia still carries them as far away as they can get. Like your blood will go as far away from your heart as it can until your skin stops it. And that's why pilots get knocked out in Top Gun. Because again, blood has its own inertia. It's going to go as far away from the center as it can until your skin forces it into the center. And depending on how the pilot is turning, that's going to take the blood out of their brain and into their feet. Or possibly all just to one side of your brain, which still isn't great. So, all that to just try to summarize what you felt when turning very fast and why pilots get knocked out if they turn too quickly. How's all that sound? Any concerns or questions about any of that for right now? All right, so main things that you should definitely know in order to be able to do homework and tests and stuff for this class. To try to summarize the main things you should definitely take away from today. Centripetal force, bless you, is a real thing that is required to make objects start turning and orbiting. So centripetal is the real one. Centrifugal force is a perception that you get when you're turning because you are a organism with multiple parts to your being that don't always do the same thing. The feeling of centrifugal force is a quirk of the nervous system and the fact that you have blood in your body. And centripetal force, the one with a P in it, is the real one that causes centripetal acceleration, and that is what's required to turn. And it increases the faster you turn or the shorter your turning radius. As practical advice goes, is that all good? An okay summary? All right. Well, that is most of today done and over with. So in our last couple minutes, I'm just going to set up what we'll be looking at next time. Does that sound fair? Just a preview. Because we got a whole week of rotating stuff to get through. Today was centripetal force. Wednesday is going to be about a different rotational concept called torque. As a word, does that sound familiar? All right. So just the setup then, to get this into your brain before next time. Centripetal force is not the only force that causes things to turn. But what centripetal force does is it takes something that's already moving in a straight line and forces it to begin orbiting. Torque is something else. Torque is what happens when you've got something that's not currently moving at all and you want to make it start rotating. When you approach this door and you want to make it start turning, what do you do with the door? When you see this, what is your first instinct about how to make it work? Push it where? Where do you apply force to the door? The handle. You tend to think to grab the handle and exert force here. The handle is a distance away from the hinge, correct? And conceptually, deep down, you have this understanding that the handle is here, this is the side of the door that I apply force on. Frankly, lots of times you might not even use the handle, but you still grab this side of the door, and you apply force that makes the door start rotating. We call this torque and not just simply force because you are applying force in a specific way in a specific direction to induce rotation rather than linear motion. Because normally when you use force, things move in straight lines, right? Linear force causes linear acceleration. But if the force you're exerting is some distance away from a hinge or a fulcrum or a pivot or something to that effect, as long as the force is a distance away from it, you instead of using normal force, you generate torque. And torque causes things to rotate instead of move in straight lines. And on Wednesday, we will be exploring how and why we do that and the many places that that shows up in your daily life. Turns out, most human tools were invented to use torque, and that does include most sports equipment. Again, that's for Wednesday. Torque is the key word for next time. Centripetal force was the key word for today. Any questions, concerns, etc. from you guys? We do have lab this week. Report to lab as normal. either today, Tuesday, or Wednesday. Lab is about friction and work. So, quarter lab is normal. If you know if you need anything